Section 2.6, continuity. Let's start off with the definition. A function f is continuous at a if the limit as x approaches a of f of x is equal to f of a. All right, in order for that definition to hold, we need three things to be true. If we want the limit of the function to be equal to the value of the function, then the function has to be defined at that point. So we need f of a to be defined. And then we need the limit to exist. And then finally, what it says up top, we need the two to be equal. So we need the limit as x approaches a of f of x, which exists, to be equal to the value of the function, which must be defined. If any of those three things does not hold, then we would say f of x is not continuous at c, and another way of saying that is to say it has a discontinuity there. So there's your definition and the three parts of it, and we'll look into an example of that. But just a quick thing to say about what does continuity look like? If a function is continuous at a point, then if you were to draw the graph with your pen or pencil, you would draw the graph through that point in a connected way without having to lift your pen or pencil off of the paper. So if it's all kind of connected as it goes through the point A, then we would tend to think of it as continuous. So let's look at that as applied to this example down here, and we'll look at it both in a visual way and then according to the definition. Let's keep the three parts of the definition handy. So show that f of x equals the square root of x is continuous at x equals 9. So first we'll start off just looking at the graph, and I've already got it set up here. So this is the square root of x, and 9 is right around here, and we can see that as the graph is drawn through the x equals 9 point, it all seems to be one connected piece, and you could draw through there smoothly. So it seems to pass that visual test of is it continuous at 9. Now let's see if it passes the more rigorous test of these steps 1, 2, 3 up above. So let's go ahead and run through those steps. First, let's look at f of 9 and see if that is defined. So f of 9 is the square root of 9, which is equal to 3. So check. It meets that first hurdle. And then let's look at the limit. What is the limit as x approaches 9 of the square root of x? Well, one of our properties of limits says that we can move it inside of square roots or radicals. So we can change this to be the square root of the limit as x approaches 9 of just x. And then for linear functions, any polynomial really, we can just plug in. So that inside part is just 9, and then the square root of 9 is 3. So the limit exists, so we can do our second check. And then notice that in both cases, we got 3. So we got 3 for the value of the function, and we got 3 for the value of the limit. So the two things are equal to each other, and that's the final hurdle. So we just can do that comparison, which we just did, and now say the limit as x approaches 9 of f of x turned out to be the same thing as f of 9, and therefore that's our final piece. So really that's the only piece you need, but in order to check that final piece, you need to see what the value of f of 9 is, which will determine whether it was defined or not, and you need to evaluate the limit, which you can only do if it exists. So you can only really make it to the third step if you make it through the previous two. All right, now let's look at something that they're saying has a discontinuity and see where in the three steps is that falling down. So show that f of x equal to x minus 1 over x plus 2 is not continuous at x equals negative 2. So let's just try and show that it is and see where it fails. So the first thing we would do is try and find f of negative 2 and see if that's defined or not. So what is f of negative 2? We're going to plug negative 2 in place of all of the x's. Then we're going to simplify, get negative 3 over 0, which is undefined. We needed it to be defined, and it is undefined. So all you got to do is fail at one of the three steps, and we failed at the first one. As soon as that happens, you know the function is not continuous there, so The fact the function was not defined at -2 means that f of x is not continuous at x equals 2. X equals -2. There we go. All right, so let's see what that discontinuity looks like if we go to the graph. So let's switch back over to the graphing calculator. I'll do the zoom standard to get the -10 to 10 window. We've got this old graph here, so let's go into the y equals and put our new one. We want it to be x minus 1, remember in parentheses around the numerator, divided by x plus 2, and then go back to our graph. So there's our graph. What happens is we approach 2 from the left. We didn't look at limits before, but it looks like that limit's going to infinity from the left side. And from the right side, it looks like that limit's going to -infinity. And that's because the function is undefined at -2 because of a 0 denominator that did not make the numerator 0. And we saw in previous sections, when you attempt direct substitution and you get a non-zero constant in the numerator and a 0 in the denominator, that creates a vertical asymptote, and a vertical asymptote will be a discontinuity of a function. So that's what that one looks like when we had a failure. And there's other ways that we can fail that continuity test, and we'll see some of those as we continue on. All right, on the previous page, we defined what a continuous function was. We had an example where we showed how to see a function was continuous at a point, and then importantly, we also saw an example of a discontinuity. And now we're going to look at the three main types of discontinuities. There are three main types of discontinuities that we will see in an introductory calculus class. The first one is known as a removable discontinuity. And that's one where the limit as x approaches a of f of x exists, which is important for continuity, right? But it either does not equal f of a or f of a itself is undefined. So when the limit as x approaches a exists, but there's a problem with f of a, either it's a different value than the limit or it's just undefined, then that's when we get this thing called a removable discontinuity. And it's given this name because the discontinuity could be removed if you were able to redefine f of a to a different value, and we'll see examples of that down below. A second type is a jump discontinuity. And that's one where the limit as x approaches a from the left and the right exist, but they don't equal each other. And we'll see examples of that below too, and you'll see why we call it a jump when you see the picture. And then finally, the third type is an infinite discontinuity, and that occurs when either the limit as x approaches a from the left of f of x is plus or minus infinity, and or the limit as x approaches a from the right is plus or minus infinity. So if either side is approaching plus or minus infinity, then you're going to have this infinite discontinuity. And typically for most of the functions we see, if we're approaching infinity or negative infinity from one side, we're also approaching one of those infinities from the other as well. And that's because these occur where graphs have a vertical asymptote. And except for special functions, it's normal if there's a vertical asymptote, you're approaching the either plus or minus infinity on each side. So vertical asymptote. All right, there are other types of discontinuities that are possible, but they're not common in an introductory calculus class, so we're not going to worry about those. So let's just get a visual on this idea. For each of the following graphs, specify the x values where the graph has a discontinuity, label which type it is, and briefly explain why it is that type. If it's removable, specify the value of f of a that would remove that discontinuity. So we're just going to go from left to right here. Notice at x equals 1 on this first graph, we have a vertical asymptote, and the limit as x approaches 1 from the left and the right is positive infinity. So x equals 1 is an infinite discontinuity. And briefly explain why it's that type. because the limit as x approaches 1 of this function is equal to infinity. So there's one of them. As we continue on from left to right, when we get to this spot right here, if you were drawing, you can't draw that as one piece. You have to jump from the height of 1 up to the height of 2. So at x equals 2, there is a jump discontinuity. I'm going to just shorten that and just put disk so that we have reason or room to write the reason. And that's because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. So that's causing that jump in the graph. So as we come from the left-hand side, it looks like the limit is 1, but when we come from the other direction, it looks like the limit is 2. So different from the two sides. All right, one final discontinuity on this graph that occurs right there where there appears to be a hole in the function, and that is occurring at x equals 3. So x equals 3 is a removable discontinuity. What we've been calling holes in functions are also removable discontinuities. So the idea there is the limit exists, but the value of f of 3 is just undefined. And we could patch that hole if we just defined f of 3 to have the same value as the limit. So why is it a removable discontinuity? Because the limit as x approaches 3 of f of x exists. It's 3. And, or I guess but, f of 3 is undefined because we have that open circle there. So that's why it's a removable type. If we didn't want there to be a discontinuity there, we could define a value of 3 to be the same value as the limit, and it would fix that. So it would be fixed or removed. Yeah, let's use the word removed. It is a removable discontinuity after all. We could remove it by defining f of 3 to be equal to the value of the limit, which in this case is 3. Now, we don't have the ability to just redefine a point here. This is somebody else's graph, and we kind of can't mess with it. But that's the value that if it was redefined to 3 would patch the hole. All right, let's just go through that same idea one more time for this next graph. Worth a mention, by the way, let's do this with the highlighter. This spot right here, this corner, that's still connected, so it's not a discontinuity. So that spot right there, that corner is also, it's an awkward spot in the graph, but it's not a place where you'd have to pick up your pen or pencil. So that's not a discontinuity at either of those corners. So where are discontinuities happening? Here's one, because it looks like we have a jump. Limit from the left is 2, and the limit from the right is 4. At 3, we've got a vertical asymptote, so that's going to be an issue. And we have a hole right there. The function is defined, but not defined in a way that fills the hole. So there's our 3 discontinuities. Let's write them up. So the first one was at x equals 2. That was a jump. And it occurred because the limit from the left did not equal the limit from the right. And then what else have we got? X equals 3 is an infinite discontinuity. And that's because the limit as x approaches 3 of f of x is infinity. And also because we have a vertical asymptote there. And then finally, x equals 4 is a removable discontinuity. And that's because the limit as x approaches 4 of the function is 4, but f of 4 is 2. Sorry, squeezing stuff in there. So I'm just going to mention it because we're almost out of space here. But the reason we have a removable discontinuity there is because the value of the function doesn't match the value of the limit. So I guess we can do some erasing here. If we were able to redefine, and so I'll do it in a different color, if we redefined f of 4 to equal 4, that would fix it. So I don't actually want to write that in there and have that wrong thing, because f of 4 is not 4, right? But if we made f of 4 4, it would patch the hole. F of 4 is in fact 2, though. That's why we have the discontinuity. All right, so watch out for those as we move forward. As we find further discontinuities in functions, always try and think in your head, what type is it? Is it removable? Is it jump? Or is it infinite? All right, moving on to that next example, we have a piecewise function here, and they want to know if it's continuous at 0. And if you look at 0, that really seems like the key thing to look at, because the function has different values depending on whether it's greater than 0, equal to 0, or less than 0. So that's kind of the most dramatic spot on the function where it can end up going different ways. You'd think if it's called piecewise, given my definition before that you draw it all in one connected piece, that it must not be continuous. But even if it's defined in separate pieces, those pieces might still connect. So to figure that out, let's try and go through the 3 steps. So we'll start off with f of 0, see if that's defined or not. So for f of 0, for that piece, let me switch the color here. That's this line right here when x equals 0, so we'd plug in to that branch of the function, and according to that, f of 0 is equal to 0. So that is defined, so we can put a check mark there. And now, because this is a piecewise defined function, and it's defined differently when x is greater than 0 versus when x is less than 0, we're going to have to evaluate the limit by looking at the limit from the left and the right separately. So let's look at the limit as x approaches 0 from the left of f of x and see if that exists and what its value is. So if we're approaching 0 from the left, that means we're approaching with values that are less than 0, which means we'd be in this branch of the function, and in that branch x is -1. So the good news is that exists, but if you're looking forward to step 3, you can already see there's bad news. The only way the overall limit is going to exist at 0 is if the limit from the left and the right are the same. And if that's the case, they'll both be -1, and it doesn't equal 0. So we can already see step 3 is going to fail. But let's go ahead and progress through this anyway. So let's look at the limit from the other side. So what happens as x approaches 0 from the right-hand side of f of x? So if we're approaching x from the right, that means we're having x values that are bigger than 0. So now we're on this top branch where the value of the function is 1. So that would be a 1. And the fact that these two are different tells us that the overall limit does not exist. So the limit as x approaches 0 of f of x does not exist, and right there, because we failed on step 2 of the continuity check, we now know that this function is not continuous at x equals 0. But like I said a moment ago, we actually knew that a little sooner, because before we even knew that the limit didn't exist, we had seen that the limit of the left side was -1, which did not equal the value of the function. So there was no way we were going to satisfy step 3 once that happened. But we really should proceed until one of the steps officially blows up, and that happened when the left and right didn't exist, because then that meant, when they didn't agree, because then that meant the overall limit did not exist, and that then violates this part right there. So once that fell apart, then we knew we did not have a continuous function at that spot. All right, let's have a look at another one. And actually, let's go ahead and look at this one graphically real quick. So what's going on there? How is it not connected? So at 0, the value of the function was 0. When x was bigger than 0, the value of the function had a height of 1. And when x was less than 0, the value of the function was negative 1. So now imagine that you're trying to draw this graph and you're coming along here and you get to 0, you have to pick up your pencil, draw this point, pick it up again, and then draw this other part. So you can't draw it in one connected piece. So that's kind of our visual of that discontinuity. All right, now let's look at that next example. So another piecewise defined function, let's see if it's continuous at 1. And it makes sense that they're asking us at 1 because, again, 1 is like that key spot where the function does different things. So let's see if it can survive that and have continuity. All right, so let's start running through the steps. First thing is, how about f of 1? Is it defined? Well, sure. The function is defined when x equals 1. The value of the function is 2. So we clear the first hurdle. And then how about the limit as x approaches 1 of f of x? I don't need to do this as from the left and the right this time because the value takes on the same function, or the function takes on the same values anytime x does not equal 1. So that includes both the left and the right-hand side. So when we're looking at the limit as x approaches 1, remember that means that x is close to 1 but not equal. So at those moments on this function, when we're close to 1 but not equal, the value of x is x squared minus x over x minus 1. Best way to evaluate limits is direct substitution if it works, but if you try and plug 1 into this one, you're going to get a 0 denominator. If you plug 1 into the top, by the way, you get a 0 in the numerator, which means there's hope we can make that 0 cancel if we factor. So let's get to that. In the numerator, can factor out an x. Denominator is already factored, but I'll just put it in parentheses. And once I do that, I can see that these two pieces cancel. So then we end up with just the limit as x approaches 1 of just the function x, which is linear and a polynomial, so we can just plug in and we get a 1. So we just cleared the second hurdle, but it's not good news. So we can put a check, like the limit does exist, but you should see, if you're really thinking about the process, you could see right away it's a problem. The value of the function is 2, but the value of the limit is 1. And we're trying to arrive at a place where both the function is defined, the limit exists, and they're equal. And at the moment we saw the limit exists, we should also be seeing, it's not equal though. So in conclusion, we end up saying the limit as x approaches 1 of f of x, while it does exist, it does not equal f of 1. And that means that our function is not continuous at x equals 1. And I'm going to go ahead and skip the graph on this one because it's a little bit hard to see, but we saw some of these before. What's going on in this function is it has a hole at x equals 1. So, and it's a hole in the sense that the function, let's look at the function real quick. Let's draw a sketch in here somewhere. So the function, when it reduces, ends up just being y equals x. So y equals x is just this straight line, right? Continuous, no problem, right? Except for it's only equal to x for values that are not equal to 1. So what does that mean? That means when x equals 1, we have a hole. So I'll put a circle there. Now, does that hole get patched? No, because the value of the function at 1 is 2, which is up here. So if you're trying to draw the function, you're coming along from the left, all of a sudden when you get to this hole, you got to pick up your pencil, come up here, and then come back down and then draw some more. So you can't draw it all in that one smooth connected piece. Therefore, there's the visual of a discontinuity. All right, let's move on and look at some more examples. All right, before we do more examples, let's go ahead and present some continuity rules. If f and g are continuous at a, then the following functions are also continuous at a. Assume c is a constant and that n is greater than 0 and that n is an integer. So if f and g are both continuous at a, then so is the sum of those two, so is the difference of those two, so is a constant times one of them, so is the product of the two of them, there, so is the division of the two of them as long as the denominator is not 0, and so is one of them raised to a power. So you can add continuous functions, subtract, multiply by a constant, multiply with each other, divide as long as you're not creating 0 denominators, or raise to an integer power, and all those things will retain the continuity of the original pieces. So, for example, x squared plus 3x times sine of x is continuous. Now, there's a small problem here. Do we really know that all those pieces are continuous? Let's think about the graphs. Y equals x squared. That's a parabola. Kind of imagine that graph. It's just a U shape. That's all connected, so therefore continuous. How about the 3x part? Y equals 3x is a line. That's all connected and therefore continuous. And then finally, how about the sine of x piece? Well, that one, if you think back to trig, just waves back and forth. So that one is also continuous. So if you create a new function by doing a product, right here, we're doing the product, and then we do an addition. If we're just multiplying together continuous functions and then adding to another continuous function, the result should be continuous. Rather interesting looking continuous, right? It's kind of a wavy function built together. So you can kind of see the parabola look in there, but also the waviness of the signs, and then it's hard to see the 3x in there, but it's blended into, but it all is still connected and therefore continuous. So that's an example of kind of putting those pieces together. How do we know all that's true? Well, you would need proofs for it. I'm going to go ahead and show you a proof of just one of the pieces, but all of them can be proven, and you can look up those on your own if you're interested. So the proof that f minus g is going to be continuous. So if f and g are continuous at a, then what does that tell us? Well, let's just start trying to get to the main piece of continuity. Let's try and find the limit as x approaches a of f minus g of x. Oops. If that turns out to be f minus g of a, then we will have shown the limit exists, that the function is defined, and that they're equal. And if we have all three of those things, we've got what we need. So one of the limit properties says if you're doing a limit of a subtraction, you can change that to a subtraction of the limits. And f minus g really is a subtraction. So let's just write that in a different way. What is f minus g of x? It's f of x minus g of x. And then again, limit properties say if we're doing a limit of a subtraction, we could do the subtraction of the limits instead. Now this is the part that may be a little bit of a big jump, but we should know that the limit as x approaches a of f of x is just equal to f of a, and that the limit as x approaches a of g of x is just g of a. Now, why should we know that? The answer is because f and g are continuous at a. And if a function is continuous at a, it means that the limit is equal to what you get if you just plug in. So because we know the original two are continuous, that's what allows us to make that leap and that leap. But f of a minus g of a is the same thing as f minus g of a, just by the definition of what subtraction of functions is. So what does that mean? That means that we started out trying to find the limit as x approaches a of f minus g of x, and we got an answer, and it was just the same as if we plugged a into f minus g of x. So the function's defined because the original continuity, the limit exists, and the two are equal. So that proves it. All right, let's go ahead and summarize something from that and then do some more examples. So theorem 2.9, polynomial and rational functions. So from the rules up above, we can conclude that a polynomial is continuous for all its values of x's, because a polynomial is just made up of values of x's raised to powers and multiplied by constants and added to other pieces that are similar. And then a rational function is just the division of two polynomials, and so that division would also be continuous as long as you're not getting a zero denominator. So our second rule, part B, says that if you take a rational function, p over q or p and q are polynomials, that is going to end up being continuous for you as long as you're not getting a zero in the denominator. So now let's use that kind of pretty powerful tool to look at this next thing and say, if you think of all the real numbers on the number line, for which of those values would f of x equal to this rational function be continuous? Top's a polynomial, bottom's a polynomial. So it's a rational function, will be continuous everywhere except for where the denominator is zero. So all we really need to do is investigate that part of it. And we could factor the numerator, but how the numerator factors is really kind of irrelevant. We just want to see where is the denominator equal to zero. So we're just trying to factor the denominator. It wouldn't hurt to factor the numerator, but it's not necessary. So what are two numbers that multiply to 12? What are two numbers that multiply to 12 and add up to 7? So we're trying to factor this. Two numbers that multiply to 12 and add up to 7. So that would be positive 3 and positive 4. So those are the two numbers that we would use to fill in the blanks here. So we'd have plus 3 and plus 4. And so now that we have that factored, we want to start thinking about what values of that denominator would make the function undefined and therefore create a discontinuity. So x plus 3 would be 0 if x was equal to negative 3. And x plus 4 would be equal to 0 if x was equal to negative 4. So those are the two values that make the denominator 0. So those are actually values that we don't want. Those are the bad guys. So this function is defined everywhere except for when x is negative 3 and negative 4. And because it is a rational function, it will be continuous at everywhere except for where x is negative 3 and negative 4. So in interval notation, we could write that as it's going to be continuous. The intervals of continuity go from negative infinity to the first of these bad numbers we come to, which would be the negative 4. And then union that with negative 4 to negative 3, the section in the middle. And then union that with negative 3 to infinity. So the function is continuous everywhere except for those two bad spots, negative 3 and negative 4. And so that's why we put the rounded parentheses here, is to exclude the negative 4 and to exclude the negative 3, but everything else is included. Because we didn't factor the numerator, we can't actually tell whether those two discontinuities are asymptotes or wholes by the work we've done. So we could figure that out by factoring the numerator. Another way is to look at the graph. So let's go ahead and do that. So we'll switch over to the graphing calculator. We'll hit the y equals key and we'll enter our function in. So for the numerator in parentheses, we need x squared plus 5x minus 6. So put that in parentheses, divided by the denominator, also in parentheses, which would be x squared plus 7x plus 12. Close the parentheses on that. Then we'll go ahead and graph it and see what's going on at those two discontinuities. So we hit the graph button. I'm in the zoom standard here, and now I can actually see that it looks like we have two vertical asymptotes, one at negative 4 and one at negative 3. So it looks like those are vertical asymptotes rather than wholes. Let's zoom on this a little bit. See some different aspects of it there. We can see those asymptotes a little bit better. And where are they occurring? You see us start to dive down as we approach 4. By the time we get to the other side, now we're on a separate branch, so there was a jump. And then as you go here, you're going up to infinity, and then you jump down to this other side. So those definitely look like visual discontinuities, and we expected that because the function wasn't defined at those two. All right, now we're moving on to the idea of continuity on an interval. And we've kind of already, we've talked about these stretches of a function where it was continuous. When there's a discontinuity, then we often wonder about, well, how about at the edges, like right where that discontinuity happened? And to investigate that, we need definitions of continuity at endpoints of an interval. So a function f is continuous from the left at a. So let's fill that in. If the limit as x approaches a from the left of f of x equals to f of a. So notice that looks just like the definition of continuity, except for we just have like from the left. And then the same thing from the right. So the function is going to be continuous at a from the right, at a if the limit as x approaches a from the right of f of x is equal to f of a. And then when we start talking about continuity on an interval, we're going to say a function f is continuous on an interval I if it is continuous on all points at all points on I, and if it contains its endpoints, we will say left continuous or right continuous at the endpoint. And what do we mean there by if it contains its endpoints? Well, remember that in interval notation, you can have an interval like open parentheses from A to B, where then it's a closed or squared off bracket. And then what does that mean on the number line? If this was A and this was B, it means that A is not included, but B is. So if the endpoint is included, like the B is, then we'd try to check to see, since we're coming from the left, is it continuous from the left? So let's look at this graph here. That gives us a little bit of a guide to that. So all this seems continuous and connected, and then we get a discontinuity at 0 because there's a jump, right? There's a break in the graph. The limit from the left-hand side and the right-hand side are not the same. But before that break, it was continuous all the way up to 0 and including 0, because the limit from the left was equal to the value of the function. But on the right-hand side, we don't include the 0 in that part of the interval of continuity because the endpoint is not included. So this endpoint right there was not included, and that's why it's not included here. The limit as we came from the right-hand side didn't equal the value of the function, which was down there. So left continuous at x equals 0, but not right. So we included the 0 in the interval that comes from the left, but not the one on the right. Okay, so let's determine the intervals of continuity for this function. So if it's continuous everywhere, that's easy, right? So let's start off by investigating where does it have discontinuities. It's a rational function, so any discontinuities that it has have to come from 0 denominators, so we'll try and factor the denominator. And to get that 2x squared, we have to have 2x and x. To get the 1, we have to have a 1 and 1. To get it to be a negative sign right there, we need these two signs to be different from each other. And we want the middle part to be negative x. So I'm going to put the negative here and the positive there. Why? Because if I do that, I get negative 2x there and positive 1x there. So by putting the negative in the second pair, I was creating a negative on the bigger product between outer and inner, which ends up making the middle term be a negative x instead of a positive x. Let's get those lines out of the way. So we now have two discontinuities, right? Coming from the denominator. If 2x plus 1 equals 0, that would mean x equals negative 1/2. That's going to be a discontinuity. And if x minus 1 equals 0, that's going to mean x equals 1, and that's a 0 denominator, so that would be a discontinuity. So these are two places where the function is discontinuous. and those are not included as values of the function, so they can't be included in our intervals of continuity. So we're going to be continuous everywhere else, though. So the function is going to be continuous on the interval from negative infinity to negative 1/2. That's not included because the function's not defined there. And then we pick up continuity again from negative 1/2 to 1, where we reach our second discontinuity, which is not defined in the function, so can't be included as part of where it's continuous. And then we end up continuous everywhere else from 1 to infinity. So there's the three intervals where the function has continuity with those 2 points of discontinuity being removed. Let's try that for another type of function. This one's not quite a rational function because of the square root. So how do we deal with that? Well, one of the things that you need is the function has to be defined somewhere for it to be continuous. And we have 2 issues here with the function being defined. We can't have the denominator being equal to 0. So if x squared minus 9 is equal to 0, that's going to have to create discontinuities. If you factor that, that's x minus 3 times x plus 3 equals 0. So it looks like we would not want x to be 3 or negative 3 because either of those create a 0 denominator and therefore an undefined function and therefore cannot be places where it's continuous. Now, the other issue that we have to watch out for is because we have a square root, we can't have the part that's underneath the square root being less than 0 because then we'd be getting imaginary numbers rather than real ones. So where does that happen? Well, the easiest way to sort that out is to make a sign chart. So let's draw a number line. Let's put these 2 discontinuity critical numbers on that number line, negative 3 and 3. And then let's just think about what happens at the various places on that number line. So let's do some testing. What if I put a number in, I'm going to switch colors here. What if I put a number in like 0? What would happen? Well, if I put a 0 there, 0 squared minus 9, that's negative 9. So that's negative. So everything in this range would also be negative, which, by the way, is something that's not allowed. That's bad, right? That violates the function being defined. How about on the outsides? What if I plug in a number like 5? 5 squared minus 9 is 25 minus 9, 16. It's positive, that's the key thing, and that's fine. That's part of the domain of that square root function. What if I plug in a number like negative 6? Then I'd get 36 minus 9, which is 27, which is positive. So all of that's fine. So the bad part is in between negative 3, but 3 and negative 3 are also bad. So those cannot be part of the intervals where we have continuity. Everywhere else should be fine. Let's just look at a different number outside of that range. So let's suppose that x is not an element of negative 3 to 3. Then the limit as x approaches, whoops, I put x, but I want a. So let's suppose a is not an element of negative 3 to 3. Then the limit as x approaches a of f of x is equal to 1 over the square root of the limit as x approaches a of x squared minus 9. As long as I'm in the domain of that function, I can move the limit into the numerator and denominator and eventually into the square root. And then at that point, because it's now a polynomial underneath, I can just plug in and get a squared minus 9. So for all values of a that aren't between negative 3 and 3, this is going to be defined and equal to the value of the limit, and therefore we'll have continuity at all those values where a is not an element of negative 3 to 3. So where is it continuous? It's continuous on the interval from negative infinity up until negative 3, but not including it. And then again from but not including 3 to infinity. So we see another issue that can cause a discontinuity here. It doesn't have to be a vertical asymptote. It doesn't have to be a hole. It could be a section of the function that's just really kind of completely undefined. Probably worth a look on the graphing calculator real quick. So let's jump over there. So let's clear out this old function. Let's enter this one in. So we have 1 divided by the square root of x squared minus 9. And let's just take a look at the graph. Let's do this zoom standard. And so let's see. Looks like we have a vertical asymptote situation at negative 3 and at positive 3. That makes sense because the denominator's 0 there. But when I try and trace in the middle, pay attention to the upper left of the screen. Remember the NaN means not a number. So everywhere that I'm moving in the middle, the y values are undefined. Only when I get to the left side or the right side do I have defined values for y. So it's that undefined section in the middle that's creating the discontinuity. All right, back to the notes and on to one more thing. All right, let's take what we've been discussing so far and try and apply that to trig functions. So for what values of x is the function f of x equal to tangent of x continuous? So to tackle this, I want to start off by thinking about what is tangent of x. Tangent of x is sine of x over cosine of x. Now, we talked about previously that sine of x is just this wave function, but so is cosine. So both sine of x and cosine of x, I'm going to just assume for a moment those are continuous based on we've seen their graphs and their connected pieces. That needs to be proven officially, but visually we kind of know that. So if we took that for granted, that sine of x and cosine of x were continuous, then when you do the division of these two continuous functions, that should be continuous everywhere except where the denominator is 0. So this function tangent, which is sine over cosine, is going to be discontinuous if cosine of x is equal to 0. So to think about where that happens, I'm always going to think about unit circle. So let's draw the unit circle. Remember the cosine is the x-coordinate of any point on the unit circle. So if I take a random point on the unit circle, that's going to be cosine of x, comma sine of x. So where on the unit circle, as I make the trip around this circle, what are the spots where the cosine, which is the x-coordinate, would be 0? That should be happening here and here. Those are the two spots on the unit circle where the x-coordinate is 0. What are those actual coordinates? This point up here is 0, 1, so there's the 0 in the x spot, and this one down here is 0, negative 1, but again, 0 in the x spot. So then the next question becomes, well, what angles are those? So you measure your angle from the positive x-axis. So if we came this way, there's our first angle. That would be pi over 2. Got a lot of writing up here, but let's squeeze it in. So that'd be pi over 2. And if you kept going, this would be 2 pi over 2, and then on to 3 pi over 2. So it looks like the two places where cosine is going to be 0, and therefore the fraction for tangent would become undefined, are at the angles pi over 2 and 3 pi over 2. But it's really also anything coterminal to those, meaning I could have gone in the other direction and got negative pi over 2 and negative 3 pi over 2, or I could make multiple laps around and stop. So there's lots of angles that stop in those same places that have that 0 value for cosine. So what are they? Cosine of x is going to be equal to 0 where? It's going to happen when x is equal to pi over 2. We kind of talked about that already. But then it's also going to happen anything that's 180-degree multiple from pi over 2. So if you take pi over 2, got a lot of scribbling on here, but we'll do some more. So here we are at pi over 2. If you go, let's switch to red. If you go halfway around, which is a multiple of pi, you're going to be at another 0 spot. If you from there went halfway around again, you're also going to be back at the 0 spot. So every time you go 180 degrees in either direction from that original spot pi over 2, you end up at another spot where the x is 0. That is a lot of scribbling, but at least we saw it in pieces. All right. So what does that mean that you can do 180-degree rotations and still be a spot where cosine equals 0? It means it could be pi over 2 plus k times pi, where k is any integer. So when is tangent continuous? Everywhere except for at those spots. So tangent of x is continuous for all x except x equals pi over 2 plus k times pi, that's adding those 180-degree multiples, where k is an integer. So what do we end up seeing there? When was tangent continuous? Basically everywhere it was defined, everywhere that it didn't have a 0 denominator. And it turns out all the trig functions are like that, and that's what this next theorem states for us. So when do we have continuity for trig functions? And the answer is everywhere they're defined. And sine x and cosine x are defined everywhere, so they're continuous everywhere. Tangent x, if the denominator is 0, you're going to have a problem. Cotangent, secant, cosecant, those are all fractions too, so they all have the ability of a 0 denominator. So as long as you don't hit those 0 denominator spots, the trig functions are continuous everywhere else, which again means sine and cosine are continuous everywhere, and the other trig functions are continuous whenever their denominator is not 0, or in other words, all the trig functions are continuous at all points of their domain. And the only domain issue that any of the trig functions have are 0 denominators. All right, so let's try and put some of that stuff together that we've been seeing so far in this section. Let's look at a piecewise defined function that has trig functions as its branches, and let's see where it's continuous. Well, sine's continuous everywhere, and so is cosine. So the only way we could have a problem is when we change from one branch to the other, and that change is happening at pi over 4. So if this function is continuous at pi over 4, it'll be continuous everywhere. If it's not continuous at pi over 4, it'll be still continuous everywhere else, because the other branches are made up of continuous functions, sine and cosine. So let's investigate pi over 4. How about f of pi over 4? So you want to plug it in, but to which branch? Well, pi over 4 is included right there. Whoops, that one a little hyper. Right there. Did it again. So that green part right there has the included, so that's the branch that includes pi over 4, so this is the place where we would plug that. So f of pi over 4 is cosine of pi over 4, and cosine of pi over 4, same as cosine of 45 degrees. If you have your trig functions memorized for the nice angles, you would know that one is root 2 over 2. So check mark. Why? Because it's continuous there? No, because the function exists there. We still have to investigate the limits. And because we have different function definition for the branch when x is less than pi over 4 versus when it's greater, we're going to have to look at the limit as a from the left, from the right situation. So let's look at the limit as x approaches pi over 4 from the left. So if we look at that, from the left means x is less than pi over 4. So we'd be looking at the branch where x is less than pi over 4. which is the sine branch. And then because sine is continuous, you can always evaluate the limit of any continuous function by just plugging in. Because we know that for a continuous function, the limit exists and equals the value of the function there. So the limit of sine of x as x approaches pi over 4 from the left can just be found through direct substitution, sine of pi over 4, which is root 2 over 2. And then if we look at the limit from the right, of f of x, because we're looking from the right, we're looking at values where x is greater than pi over 4. So we'd use the branch of the function, cosine of x, which is defined for the x greater than pi over 4 piece. So that would be cosine of x. But again, cosine's a continuous function, so you can figure out its limit, in this case from the right, but whether it's from the right or the left or whatever, for a continuous function, you can evaluate the limit by just plugging in. Direct substitution always works on continuous functions, and that's root 2 over 2. So the two are the same. That's really crucial. So if the two are the same, that means the overall limit exists. So we now know that the limit as x approaches pi over 4 from either side always ends up being root 2 over 2, but we also know that that was the value of the function because we checked that at the first step. So the limit is equal to root 2 over 2, so is the value of the function. So the limit equals the value of the function is defined, the limit exists, we've got all the pieces we need, and that implies that we have continuous at pi over 4, and that was the only part we were worried about. So if it's continuous at pi over 4, it's going to be continuous everywhere. So f of x is continuous on the entire real number line. I think that's our first example of a piecewise defined function where the two sides are connecting up. So we are getting continuity despite the fact that it's defined piecewise because, and we're kind of seeing this in the limits, the limit from the left collided with the limit from the right. So what that means is the cosine function and the sine function meet up at that point. So even though we're defining the branches different on the two sides, because they connect, we're okay. All right, let's go ahead and wrap up this section with a theorem and then an example that illustrates the theorem. So the theorem is called the intermediate value theorem. Suppose that f is continuous on some closed interval from a to b, and that L is a constant between f of a and f of b, with the heights of f of a and f of b not being equal or not being the same. So on this illustration over here, there's our f of a and f of b, and they're not the same. And here's a height L that's in between those two different heights. So that's what they're talking about. The other thing they mentioned is that the function is continuous, so switch my shading color here, but in between those two heights, you draw from one to the next in a connected path. So if all of that's true, then they're saying there has to be a C somewhere in the middle, open interval from a to b, such that if you plug f into the function, you get that height. So in the illustration, here's that C. It's somewhere in between the a and the b, and when you plug it in, you get this height, which is equal to L. So there's a picture of it. And it makes sense that this is always going to be true, I think, because if you have a continuous function, you're drawing from one end to the other without picking up your pen or pencil. So if you go from a high point to a low point, so I'm going to trace that through in a different color. So we're going through from the high point to the low point. You have to take on all heights in between. That's the intuitive idea of a continuous function. So let's see what that looks like when we apply it to an actual function and kind of how we would look at all the pieces. Show that there's a 0 for the function f of x equal to x to the 5th minus x squared plus 2x plus 3, somewhere on the interval from -1 to 0. All right, so we want to apply the intermediate value theorem. So first of all, let's make some notes about continuity. F of x is a polynomial, So f of x is continuous for all real numbers, which implies that it's also continuous on any interval whatsoever, including the closed interval from -1 to 0. So having the function be continuous on the closed interval we're talking about is a required piece, and that's going to definitely be true here because it's a polynomial. And then the next thing we want to look at is what about the heights of the two ends? So what is f of -1 and what is f of 0? Well, to get those values, we just need to plug in. So -1 to the 5th minus -1 squared plus 2 times -1 plus 3. So if you work all that out, it ends up being -1 for the height. What if you plug a 0 in? 0 to the 5th minus 0 squared plus 2 times 0 plus 3. All those pieces with the zeros go away. We just end up with the 3. All right, so now they want us to show that there is a 0 somewhere in between -1 and 0 on that interval. So 0 is, to say a function has a 0 means that the output is 0 somewhere. So then when they talk about the 0 there, they're talking about the L. And if you look back at the theorem, what do we need to show? That L is between f of a and f of b. So let's check that piece. 0, which is the L they're talking about, that is in between -1 and 3 for sure. And then -1 was f of -1, and f of 0 was 3. So we do have the idea now that L, 0, is in between the two endpoints. So let's see where we are on the intermediate value theorem. How much do we have? Are we there yet? So when you're trying to use a theorem, you always want to try and show that you have all the if pieces, and then you get the then for free. So they didn't use the word if, but they used the word suppose. So we need all those suppose parts. Did we show that f is continuous? Yes, because it was a polynomial. And then did we show that we had a number that was in between the two endpoints? Yes, 0 was in between f of -1 and f of 0. Okay, we've shown all of the suppose parts then, so we get the then part. So there, according to the intermediate value theorem, there is a c somewhere in the open interval. So let's write that down. By the intermediate value theorem, there is a c somewhere in the open interval, which is going to be for the two inputs we had, -1 to 0, such that f of that c is equal to whatever the L was, but the L, in this case, was 0. So, a whole bunch of pieces there. We showed that we had a continuous function. We showed that 0, which is the value they wanted us to prove the function takes on between -1 and 0. We showed that 0 lies in between the heights at the two endpoints of the interval in question. And then by the intermediate value theorem, we could say there has to be some number somewhere in the middle of that interval such that f of c equals 0. And if plugging that number into the function makes it equal to 0, that means that c is a 0 of the function. And that's what they wanted us to show. And again, that 0 was in the interval that they were asking for too. So the intermediate value theorem has guaranteed us that this function does have a 0 somewhere in between -1 and 0. So now they want us to use the TI-84 to approximate that 0. So I'm going to use my iPad version of the TI-84, which actually makes this a little bit too easy, but I'll still describe the process on the regular TI-84 as well. So what you want to do is plug the function in. So I did that already. X to the 5th minus x squared plus 2x plus 3. And then you want to graph it. And then just make sure that your graph goes from -1 to 3, that you can see, or sorry, -1 to 0, because that's the interval they're talking about. So there roughly is our height, at 0, and then somewhere right around there is our height at -1. In fact, there it is exactly if we look upper left, -1, 1. And then you can see somewhere in the middle it crosses. And when I'm tracing on this calculator, I get this really cool feature of when it hits a 0, it kind of locks in on it and turns red and shows you what the exact value is. So I can see right there what the 0 is. I just look to the upper left, and the x is approximately -0.8707 is when the y value is equal to 0. So I'm going to go write that down, and then because your calculator is a little different, I'll describe like what your process is going to be. So x is approximately -0.8707. And notice that is in between the -1 and 1, which is what the intermediate value theorem guaranteed. So on the TI-84, what does that process look like for you? So graph the function. And then look for, on the calculator screen, an option that says calc. And from there, look for the option that says 0. After you do the calc 0, and by the way, the calc key is right above the trace key, and then you'll choose the 0 option. And then the next is going to ask you for a lower bound. So you can just put, in this case, you could put for the lower bound -1. But what you're always doing is whatever the left endpoint of the interval you were given is. And then for your upper bound, you would put the right-hand end of the interval you were given, which in this case was 0. And then after that, it's going to ask you for a guess. And it really doesn't matter too much for what you put for the guess. Just put any number in between. So guess anything in between. And again, really, you don't even have to type anything there. When it asks you to guess, just press the enter key, and it should show you the 0. So it's nice the way it does it on here, and I just use my finger and I scan across, but you can do it on the TI-84 as well. Graph the function, above the trace key, hit second calc. There'll be an option there for 0. It'll ask you for your lower bound. When it asks you for your lower bound, just put whatever the left-hand side of your interval is for the problem. When it asks for the upper bound, give the right-hand side. When it asks you for a guess, put anything in the middle or just press enter, and it'll lock in on the x for you. And then round it to however many decimals the homework wants. All right, that was another big section, but we made it through. Hopefully you're still here with me at the end. Good luck on the homework.